All right, welcome back, folks. Good to see you all. So, in our last coding lecture, we were coding up what, my friends? And I'll give you a hint. It was at the little ticker scrolling at the bottom of our little intro. What were we coding up? What kind of controller? That's right, a model predictive controller. Yeah, it's model predictive control. Okay. Now, again, just as a refresher, the idea of model predictive control is basically, what if instead of doing a trajectory optimization one time, okay, or you come up with a plan, that's my plan, I'm done. What if we could do it all the time? What if we could do it all the time? Okay. That's the core of model predictive control. And what we were coding actually pretty far along in coding up our example of a model predictive controller. Okay, and so what I'll remind you what we had. So we started this model predictive controller, and the idea is we were going to do this sort of curling problem. Okay, really it's like a hockey puck, right? So it's a hockey puck that we are trying to maneuver from one place to another, from here to target, right? Okay, and so we wanted to maneuver to the target, and we had some force limits on here. And basically, what we were coding up from scratch, mind you, was all the components that we need for model predictive controller, which were the dynamics. Oh, look, there's the dynamics from our lecture last time. You know, just F equals MA stuff, simple first double integrator dynamics. We had a little double derivative there. Okay, came up with our state vector to get our state space form, where we have, you know, x dot, or in this case we called it z dot for our state because x is foolishly taken already, is equal to a function of your state and your input, your state and your input. Then what we did is we put it into LTI form, into an LTI state space form. LTI, we all know, is our linear time invariant system. So basically we turned it into, our dynamics are equal to some matrix full of constant values that are not time varying, so time invariant, times your state, plus B is another matrix times your control input. There's your state equation for your LTI system. All right, which we can compute via the Jacobian, and we kind of did it by hand here. Come up with an A matrix and a B matrix. And with that LTI system, we were moving on to MPC, where there are basically three key steps to MPC. One is you sample your current state, because MPC, this model predictive control, it is a closed loop or feedback control. It senses the state that you're in, and then it adjusts it adjusts the control input accordingly. As opposed to trajectory optimization in and of itself, is often just a feed forward or open loop trajectory. Okay? Then we formulated trajectory optimization with our current state as our initial condition and solve it. And we use direct collocation. Probably the most popular way to do model predictive control is with direct collocation or some very similar method. You could do it with single shooting, you could do it with multiple shooting. Well, what's one of the reasons that we want to use direct collocation for model predictive control? Can anyone think of an advantage of direct collocation for model predictive control? Feel free to type it in the chat and I can call it out loud, whatever you want. You are correct that direct collocation takes into account the dynamics of the system. That is true, but technically so does single shooting and multiple shooting. But they take it into account in different ways. The shooting methods do a time marching simulation, right? Direct collocation has these physics constraints built into the optimization problem. The simulation one takes longer. It's going to take longer in general to simulate a system to see how it goes and then optimize, right? And is time important in model predictive control? How much time it takes to solve your optimization? It is. It's very important because you could only you can only determine what control input you want as fast as you can solve this optimization problem. Crazy. Crazy. So direct collocation is faster to solve, especially when we have an LTI system. Especially. Okay? Then, once we have our optimized trajectory, we execute that trajectory. We use the first little bit of that trajectory for TS seconds, and we continue. Okay? So we set up our trajectory optimization problem. We had it here. Just as a reminder, we had all of our decision variables. All of these notes are, of course, up on the canvas. Also, I recommend the code from last time is up on canvas. We will be building on top of that code today. If you don't already have it, feel free to go download it. Yeah, and if it's not up there, please let me know, but it should be. If there's ever a piece of code that's not up there, let me know. I think there's only one lecture. I believe it was the constraint minimization lecture. I think I wanted to make some changes to, but that has not been evaluated part of the course. It's just, and we got here. So once we have our dynamics, here are those physics constraints, the things I was talking about for direct collocation, sometimes called the defect constraints. Okay. So we said, and so for a trajectory optimization problem, you had to have your constraints. There are physics constraints. We also have initial condition constraints here. We have and bounds on all of these values and all nodes. Okay. And this was our cost function. And our cost function is determining how we're getting to that final position. Okay. This is the only thing encouraging our system to go to the final position at this point. And the way we encourage it is by saying, hey, where we want to go versus where we are, subtract them, square it. Square it. Okay? All right. What are these terms here? What do these do? Fx squared, that's force. Fy squared, force. What does adding those terms to the cost function accomplish for a model predictive controller? Anybody? Anyone have an idea? Why do we have them in there? What does it do when you have these forces in the cost function? It keeps the forces small. That's right, Jack. That's right. It's trying to keep the force as small as is reasonable while also trying to hit the target. So it balances these two things. Okay? Boop, 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 boop. Great. So here was our code. We had some main script, which we had some crazy name for. All right? And it has a loop that samples the state, runs the trajectory optimization, and then the idea is it would simulate our system for TS seconds. These are the 3 steps for MPC. Okay? And running the trajectory optimization required solving a quadratic program, an optimization problem that happens to be quadratic. Okay? So we set up an optimization problem. You'll recall all this. And we actually managed to solve it. So I'm going to pull up, this is where we left off last time. I'm going to pull up our trajectory optimization from last time. So you can see here we have our code. Here's the script. Okay. And we have it set up so we clear everything. Here are our model parameters. This is where we defined our dynamics. There was that A matrix and that B matrix. Let me give myself a little bit more space so my nose isn't blocking the view. There we go. Perfect, right? There's our B matrix, and then our dynamics function is AX plus BU, or we just happen to call it Z because X is already taken. Okay, all right. We set up our trajectory optimization problem, where N was the number of nodes or knot points on the spline. Okay. This is a matrix of states where each column is a state vector at a given node And same thing here where this is the matrix, this is a matrix of inputs where each column is a control input vector at a given node. So you can see that we have 2 control inputs, so we have 2 rows, and we have n columns because we have n nodes. These are the points along our spline. Okay. Now there is one tricky thing we did here. We might have done it a little bit faster than I might have wanted to at the end of last lecture. I was still delusional we could finish everything in one lecture, but you know, lecture and a half, we'll see. Okay. And see, this defines our decision vector. And what it does is putting all of our states and inputs, our decisions, into one vector. Okay? So the reshape turns the matrix it's given into the size we want. That's what it's doing. So it's taking, hey, here's our USIM, this is that giant matrix. I transpose it just so this is just a trick I do to transpose it. So that way all the things I want to happen first are in a column. And then it reshapes it into a 2n by 1 matrix. A by 1 means 1 column, so it's a column vector, right? So this is a column vector. In fact, what I'm going to do is I'm going to take this and I'm going to clean this up a little bit. I'm going to cut that. I'm going to say this is all of our, this is a control decision. So we'll say this is our decision vector control column. This is very long, I apologize. Is equal to that. And this is our decision vector. So this is going to be our decision vector state column. And it's equal to all of this. I'm going to cut and paste it, put it onto this line. There we go. Boom. So that way you can see what this is doing. This is just taking the decision vector control column, and then right underneath of it is going to be our state column. There. That's all that's doing. Okay? So in case that notation is probably a little opaque to you all, right? Okay. Then we define our cost. Okay. This here is our time horizon in seconds. Okay. The model predictive controller is going to look some time into the future. Some finite time. That's all. Some finite time. And I decided it was going to be 2 seconds. Why? Because I said so. You can choose it to be different if you'd like. Okay. Absolutely. So, yep. And here is our cost. Now, you can sort of compare this cost. Let me zoom in on our cost from the notes, point by point here. There's the cost in the notes. And this here is a sum of all of our first column of ZSIM, first row of ZSIM, because it's the first row, every column, minus the target, and we square every element. So what's happening here? Let's see. Let me see if I can actually show this off here. Let's keep it on here. So basically, this is saying, hey, all of our x positions, which is our first state, minus our target, we're going to square each and every one of them, and then we're going to sum them up. Kind of like an integral, right? This is just a rectangular integral, okay? But one thing you might notice is that we're going to take every single value, it looks like in this. It's just sort of a quick and dirty cost function. We'll fix it later. But it's going to count every single state, x at the very beginning and x at the end. That's okay. Here it's going to take our third state, and which is y, and subtract it from y target, square them all, and it's going to sum them all up. And then we're going to add to it all of the control inputs, 1, comma, colon. Okay, all the control inputs we're going to want to minimize. Okay. There was some talk last time that would you want to do a, so this is basically a forward rectangular kind of integration, like you're learning calculus 2. We'd probably be better if we did a trapezoidal, but we can do that a little bit later. This is probably good enough for now. And then we get multiplied by delta t. So what I'm going to do is just make this a little bit more clear. So I'm going to create something called dt, which is the time between each of our nodes. So recall, and just draw here at the bottom, the time between each of our nodes. Here we've got time. Let's say we have some control input, or it's a state or something. And here we have all of these node points, right? And this final time here is t. There are n of these nodes, right? So therefore, the distance between them could be called delta t is equal to t over n minus 1 for reasons I've said a bunch of times. Okay? So just to make it clear up here, I'm going to say is equal to t divided by n minus 1. So it's just dt. All right? This is our cost function defined in terms of symbolic decision variables. This allows us to compute Hessians and gradients symbolically. Okay? Which is literally what we do here. The Hessian and the gradient. And as a reminder, I'll pull this up on the big screen. So recall, for a general optimization problem, a general program, we're going to say that our optimal decision vector W, is our optimal, is going to be equal to the argmin, or the input argument W that minimizes our cost function. We'll call it f of W. That's our cost, subject to a bunch of constraints. I'm going to skip over some time here. I'm going to say G of W is less than or equal to 0, and G EQ of W is equal to 0, right? General optimization problem. Okay? But it's one thing that's nice about this cost function that we have is you have all these terms that appear to be squared values of our decision variables. So therefore, our cost is likely quadratic, and in fact it is. So, which means that for a quadratic program, the form was W star is equal to argmin of 1/2 W transposed HW plus C transpose W, where H was the Hessian. Again, the Hessian, that's the second derivative with respect to the variables. And this here is the gradient. Now, so we have a quadratic cost. But to be a quadratic program, you would need your constraints to be linear. Okay? So we say subject to the constraint that A, and I'll call it A con to distinguish it from A for the state space form. Okay? W is less than or equal to B con. And A con we'll call it EQ for the equality constraints times W, must be equal to B con EQ. So these are linear constraints. Okay. All right, and you have a quadratic cost. Therefore, it's a QP. And if this Hessian is what we say is positive, it's called positive definite, then we know it's convex, and convex is good. Okay? That's exactly what we have here. So we computed our H and our C. And voila, we have our cost function in terms of a quadratic program. I set my simulation time parameters for how long we want to run the simulation here. We have, and this is our initial condition. For the simulation. Okay. Now here we came up with our physics constraints. Recall that these physics constraints, they are formed via direct collocation with basically using an explicit Euler or a forward Euler's method, where we say that the next time step is equal to the previous time step plus the derivative at that time times delta t. Euler's method. Remember Euler's method, particularly forward Euler's method. So this would be forward Euler's method. This is just a little review of what we did last time to catch everyone up, okay? And here we go. We have what I call EQ con, which are all the equality constraints put together in one vector. Look at that. We commented that nicely, which is all of our physics constraints and all of our initial condition constraints. Notice that our initial condition constraints here, we said, hey, the first state vector minus our initial conditions, I guess for the, this is the initial condition for the trajectory optimization. Apologies. For the trajectory optimization. Okay. Is equal to, that minus that is equal to 0. That must be true, right? This is that's our equality constraint. So we then take the Jacobian and then we find the constant terms, and that gives us our A con EQ and B con EQ. These things right here for our linear constraints. We take the Jacobian to get A. All the terms that are left over that aren't captured by the Jacobian, that's the B, just like you did in your homework. Okay? We then converted all of these symbolic variables to be floating point values and ran the trajectory optimization. And we're like, oh my goodness, we did it. Let's run it. Let's run it and see what happens. Okay. And sure enough, we did a trajectory optimization, and I plotted the X position and the Y position over time, and it starts at 0, 0, where we'd expect, and it's trying to move to the upper right. And sure enough, you can see the little points there. It's moving in the upper right. So basically, we did steps 1 and 2 of model predictive control. We said, hey, what state are we at? 2, make and run a trajectory optimization. 3, execute on it and simulate. So we need to do step 3. So what we need to do is we're going to save a new copy, okay, of this. We're going to say save as. We're going to call it run mpc.m. Okay, run mpc. Okay, so it's just going to be called run mpc. Run mpc right there. All right, and a new date. It's a new day. It's a week later. Okay, we're going to keep all this stuff. Just run mpc. So we have to do a few things. One, we need to be able to run this simulation. We need to run this optimization inside of a loop. So we need a loop. Okay? So, I And we're going to start our loop. Where do we go? Where do we go? Where do we go? Right above where it says constraints here, we're going to create our simulation loop. Okay? This is where I'm at right here, right above constraints. All right, we're going to try putting it right here. This is not going to be an optimal placement for this in the code, and I'll show you how we can improve it later. Okay? So, we need to create our simulation loop. So, what's going to happen is that each sampling time, TS, or I guess what we call, where is TS? We call it DT in this code. We sample the current state, Z0. That's step one. Actually, we'll make this exactly like the MPC steps, right? Number two, we set up and run the trajectory optimization. Now, the trajectory optimization will be dependent upon what Z0 is, right? Because we need to know where the trajectory optimization is supposed to start. And then three, we execute the trajectory for TS, or in this case we call it DT seconds. So how do we do that? So first we're going to do a loop. Okay, we know that we have a time span. So let's say, I'm going to say for iter, do a for loop, and we're going to iterate from 0 to 10 in increments of dt, right? All right. So how are we going to do this? So let's say we want our, here will be our t. How are we going to do this? How are we going to do this? We're going to say our time current, our current time, it's going to be where we want the simulation to start. In this case, the time spans from 0 to 10. So we want that first element, so that's t span 1. T span 1. Okay. Okay. And we're going to say for iter, how many times do we want to iterate? Okay, we're going to iterate from 1 to the number of elements of 0, TS seconds in the future, TS seconds in the future, or sorry, DT seconds in the future, all the way up to 10. So 0, DT, 10. Right? So these are all the different time steps that we're going to run for we execute a trajectory, right? Okay, D capital T. Right? So at each sampling time, do we say, hey, what is our current state? We already know our current state is Z0. So at the end of the loop, we will update it. Okay. Then we need to set up a trajectory optimization. And right now we have it down here. Okay. We're setting, what happens is every time we have a new Z0, what does that change? Well, that changes, this constraint right here. See that? Z0, the initial condition constraints. And this is going to be changing every part of the loop, right? Because every time we do a loop, we're going to change that current state, right? Boom, 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 right? I'm glad you agree. So here we are we are updating the constraints. Okay. And this is all inside the loop right now. We put all the equality constraints together, get all the symbolic variables, and run the trajectory optimization. We did it. We get W star, right? Okay. Great. Now we need to simulate our dynamics. So we'll say this is right here. We have it. Oh, look at this. Z0, dynamics call, T-span, Z0. But we're not running for the entire T-span. We are running from time current to time current plus dt. All right? I'm going to subtract a really small value for reasons that might not be clear right now. But I'm going to say 1e minus 6, like a millionth of a second. All right? Just not quite all the way there. The reason is what we're going to do is we're going to want to keep stacking all of these values on top of like in a vector. I don't want any repeated values because the next simulation is going to start at this time and the previous one's going to end at that time, and I don't want any repeated time points. That's mostly a problem when you want to do animation, do interpolation, which we do a lot for animation. So just save yourself the trouble, subtract off a little bit. Okay, Z0, and there's our initial state. Okay, and it simulates it gets our T out and Z out. So this changes our T span. In fact, this is pretty sloppy, so I'm going to cut it, and I'm going to take it out. I'm going to say T span iter is equal to that. That way it's just T span iter, so just this short period of time. So this is our time span of 1 TS or DT, right? And once we're done, we're going to say our T current, our current time. We've simulated for DT seconds, so we're going to say T current is going to be equal to T current plus what, friends? DT. Okay. Update our current time after the simulation. Okay. There are a couple things we still need to change, but I want to point out that now we've simulated the dynamics. Let's end our loop. What we're going to say is we're going to update our current state. Okay? Which is Z0, right? And so the current state is now what happened after you simulated for DT seconds. The very, very, very last time, the very last time, okay, is our current state, right? So what is that? That's going to be Z out. And the way that ODE45 works is you're going to look down at that very, very last row, and that very last row, or end comma colon, is our current state. Only problem is that is a row. We want it to be a column, so of course we transpose it with dot transpose. So this was the final state at the end of the simulation. Okay, so in a way, this was step one of our process. Sample the current state, then we go back to the beginning, we do a trajectory optimization of the loop, and then we do our simulation. Okay? But one thing you might have noticed is that we ran a trajectory optimization, but this ODE45 simulation has no idea, does not seem to have any clue what came out of the trajectory optimization and what to do with it. All right? So what we need to do is have our dynamics be fed in the control inputs that came out of W star from our trajectory optimization. So let's find where we define dynamics call, and let's change that. So let's go find dynamics call. Where's dynamics call? It's going to be up higher, right? Here we go. Here we go. Oh, look. You see this? Dynamics call. It's a little inline function that we made that takes in time and state. Okay? But what it calls our dynamics function, up here, nice, with time, state, and control input. And it defines control input right here. Now, just as a starting point, we said, hey, we want our control input to be 0, 0, just to try it out. But now We want our control input defined by what? Our trajectory optimization. So what I'm going to do is I'm going to take both of these lines, I'm going to move these into the loop. So I just control X these, I cut them, phew, and I am pasting them right above simulate our dynamics, or right below that. So I'm going to make some space here, paste them in there. Look at that. Okay. These are our control inputs from the trajectory optimization. So, but they're no longer 0. They're stored somewhere in W star. The question is, where in W star are they stored? Well, let's go find our definition of the decision vector, the way we had everything split up. You can't really see that too well, so I'll make it full screen. Okay? You'll notice that we had, here's our decision vector W, and our very first node was the very first force input, Fx. So the first element of W is the one we want, right? So W1 is going to be our force X. So let's go back here. So W star, which is our optimal decision vector, 1 is going to be our first force value, right? This right down here. Okay? Then you have 1, 2, 3, 4, 5, 6, all the way up to n of those, right? And then you have Fy1, your very first y value. Okay? Your y input force. Therefore, that's what we want instead of here. So that'll be W star what, friends? What goes in here? N plus 1. There are n of these, so the next index is going to be n plus 1. Done. So that means every loop, we redefine our dynamics call, so that way it calls our hockey puck dynamics with this new control input. Okay? This is our dynamics function with control input U. Okay? Other things we still need to clean up. And by the way, anyone can pop in at any point with questions, just to make double sure people know that. I hope people are following along. Right now, Z out is going to be overwritten every single time. So you want to store all the Z outs into one big long vector. The quick and dirty way to do that is just to take a vector that just keeps adding to the end. It keeps appending each column. Kind of a quick and dirty way to do it. It requires some reallocation. It's not a huge deal though. So let's do that right here, right at the top of create our simulation loop. Let's say we have something called tsim, which is currently empty, and zsim, which is currently empty. This is a running list of all simulation times from all ODE45 calls. And here we're going to have a running list of all states, simulation states, from all ODE45 calls. So every single element of the loop. So every single element of the loop, we're going to take this and we're going to append to the end of it the previous, the most recent simulation data. Okay, we've done this trick before. But let's go down here. Let's just append simulation data to the lists. So we're going to have tsim. Was it t underscore sim, right? Is what we called it. Apologies. Yeah, t underscore sim is going to be equal to t underscore sim, but beneath it you're going to have all of our t outs. Okay, and then you're going to have z underscore sim is going to equal to z underscore sim, z out. What did I just do there? Okay, sorry, force of habit. You'll notice that my indentation was wrong because it wouldn't cause an error, but for readability, I had no indentation before it. So just as a muscle reflex, I hit Control A, and then I hit Control I. You have something similar on your keyboard on a Mac. I'm on a PC right here. Okay, let's say I screwed up the indentations here, right? I want to, and so I've on this line I hit Control I, boom, it resets the indentation. It's perfect. I add a bunch of tabs I don't want. Control I, automatically indents. So if you hit Control A, Control I, does everything. That's all I did. All right. Okay. So it's appending the simulation data to the lists. So now all I want to do is I want to, instead of plotting Z out and Z, I'm going to want to plot Z sim and Z sim, because the whole first column is going to be our X position. Our whole third column is going to be our Y position because they are first and third states in the state vector. I'm going to comment this out. I don't want that right now. I'm going to run this optimization. It might take, I'm going to run this code. We'll see if it throws an error, but it's definitely going to take a little bit of time for reasons I'll explain. Okay, you'll see, look, it's running. The people were seeing minimum found that satisfies the constraints popping up over and over again. Do people see that? Get that out of the way. Is anyone getting this? Nobody? Okay. Let's see. Is it still running? Still running still. Here we go. All right. So it finally ran. It took a long time for reasons that are not fundamental to MPC that we're going to fix. But I get this line. This is the path of our object over time. Sorry, in space. X position, Y position. Okay? I see it got all the way up to 3 and 1.45. Okay? And we're trying to hit a target of 5 and 1.2. So it was on its way. It was on its way. After simulating for how long? 10 seconds. 10 seconds. Okay? Now, we did not include inequality constraints yet. We can add that in a moment. But we have a more fundamental issue here. Okay? It's actually working. Like, you could take this and make it run for longer. You could run it for 20 seconds, and it would probably get closer to the final position that we want. This block's going to move in that direction. Okay. But what's happening here is that it's taking a long time to run because of these lines of code right here. Okay? We are updating the constraints every single loop, and we have to do that for our trajectory optimization because our constraints change. Particularly our initial condition constraints right here. This Z0 changes, therefore my constraints change, therefore my AEQ and BEQ change, so I have to keep recomputing those, right? And this is currently using the symbolic toolbox. So the symbolic toolbox, doing these symbolic operations, is very helpful, but it's slow. It's too slow for control. You don't want to be doing symbolic math, doing substitutions, computing Jacobians via taking derivatives inside of your control loop. It just takes too long. So we have to move it out of the loop, but at the same time, it needs to be updated in the loop, right? Okay. So how do we solve this problem? Well, let's first see, is there anything that we can do to get things out of the loop? Well, number one, our Hessian and our gradient, they are in no way dependent upon Z0 that's changing. So we could do this calculation. We could do that we could do this outside the loop. We could do that outside the loop. Can we get these things outside of the loop? The answer is yes. Okay. What we want to be able to do is have MATLAB do all of the derivative taking that you need for your Jacobian and your substitutions, and do that outside of the loop, but you want it to leave z0 here as a variable. Therefore, and what you want that is some kind of function that you take in this initial state, and out pops a-con and b-con. That's what we want, okay? Now, we have a way to compute functions from symbolic variables. It was a function in MATLAB called MATLAB function, to be a mouthful, okay? It was called MATLAB function. We used this previously, okay? So basically, MATLAB function creates a MATLAB file or anonymous function of a symbolic expression, or a sim, okay? So what we're going to do is we're going to take all of this math that's inside the loop currently, and we're going to paste it, cut it and paste it outside the loop, all right? So everything, let's say the constraints here, everything from constraints down to here, okay? We are going to cut. So constraints down to here, we're going to cut, we're going to move it outside the loop. Okay, and we're going to put it right here above, I guess below simulation parameters. Yeah, okay. So what we're going to do is actually we're going to go above simulation parameters. All right, we're going to put it here. Okay. And you can see I cut and pasted it right underneath the Hessian and the gradient. Here we have all our constraints. What happened to all my indentations? They're bad. I'm going to get Control A, Control I, and auto indented everything. Sorry, and also went down to the bottom here. So right now. So good, we have all our physics constraints. But here's the thing. Here we have Z0, right? We don't want this to be a constant like we have down here with 0, 0, 0, 0. We want this to be a variable, a symbolic variable. And what this is going to allow us to do is create a function where we put in our initial condition and out comes just a matrix A and a vector B. That's it. So what we're going to do is we're going to instead say, right above initial conditions, we're going to say, call this Z init is going to be a symbolic vector. So symbolic vector, it's going to have 4 elements. So we'll call them each Z init. And we want it to be a 4x1. So this creates a 4x1 vector of symbolic variables. Okay. So if you were to run this if you were to take that code command and run it outside of the command window, you can see what it does without the semicolon. Here it creates symbolic variables, Z init 1, 2, 3, 4, right? Okay. So now what I'm going to do is I'm going to replace Z0 with Z init. Okay. So now my initial condition constraint now has these variables for our initial condition, right? In fact, what I'm going to do is I'm going to put a little breakpoint in the code right here so it stops. I click there on the side. So I want to show you what's happening here. So I stop the code right here. And if you look at B con EQ, which is our vector associated with our equality linear constraints, it's mostly zeros, right? Mostly zeros. Not crazy. But here, look at this. Z init 1, 2, 3, and 4 are in it, right? Those were our initial conditions. So all we need is to create a function where if we input our initial conditions, out pops the vector, but instead of Z inits, it has our numbers for our current initial state. So how do we do that? Let's go here. Let's get rid of this little stop command right there. I just clicked on the thing. Hopefully you can see it. Now I unclicked it. All right, stop the code. So once we've defined a con EQ and b con EQ, honestly, the only thing that changes is b con EQ. But we can do this where we want to create a function. We'll call it a con EQ function is equal to MATLAB function, where we create a function out of the expression a con EQ. Okay. And I believe this, let's try running this, see what happens in the command line. Here we go. This is what it gives you, is it just basically gives you, in this case, is a big A matrix. That's actually pretty easy. Okay. Yeah. So I think we're good there, actually. But regardless, so inside of a con func, there is no initial condition. But if you want there to be an input, so there won't be an input to that function. But if you want there to be an input, what you say is you want your z init to be your inputs to it. Okay. Now, one trick for the MATLAB function, if you just want to give it in as just one vector, put little curly brackets around it. This is just syntax for MATLAB function. Okay. So basically, if I run this, say, hey, what's a con EQ func? All right. It now is a function that takes in a single input variable. Okay. And that's going to be our vector of input states, our vector of initial states. Now let's do the same thing for b con EQ, but it's a function. MATLAB function, b con EQ. The variables that it takes in are, again, just the initial condition, z init. I'm going to run this in the command window so you can see what happens. You can see that b con EQ func here takes in a single variable, which is going to be our state vector, our initial state, those 4 initial states. And I'm going to scroll all the way to the right. Oh, look at this. Look at this. Down at the very end, it takes in that very first value and says, oh, I want the first element of your input. Hey, that's the first state. The second state, the third state, the fourth state. MATLAB created this function for us to call. And calling this function is super fast. It literally is just saying, oh, what's the input? It's this? Okay, spit back out this. That'll take no time at all. Okay? So, my friends, what that means is we no longer need these down here. This is no longer necessary. This is where we define a con EQ as being equal to our symbolic expression. We turn it into a double. No more. Gone. We don't need those two. We're instead going to define that in the loop via these functions we just made. So let's write this out. So this creates inline functions that quickly return the A EQ con and B EQ con matrix and vector respectively. Okay? So that means that inside of the loop, we need to update the constraints here by just saying that, hey, A con EQ is just equal to A con EQ, the function that we made, and we give it the current state, which is Z0, semicolon. And B con EQ is equal to B con EQ func, where the input is our current state, the initial state of the trajectory. Okay? So if you run this, We're no longer doing symbolic operations like the derivatives. We're not doing substitutions. We're not doing solving for equations in the loop anymore. This is the loop. Okay, what does it do? It figures out what your constraints are, solves a quadratic program. Is the quadratic program fast? Probably. Then you simulate your dynamics. And then you repeat. So if you run it, look how much faster that was. And we didn't even have an error. I feel like I should be making more mistakes. Okay? Right now it's just a boring line. We'll fix that. But we have model predictive control, my friends. This is actually a model predictive controller. I don't know if you believe me. Okay? We're going to have to make this fancy, though. But any questions while I move on to the next phase, we'll do it. We'll make some changes. For instance, I'm going to make the time span. I'm going to make it longer because it doesn't take very long to simulate. Make it 20 seconds. Run it for 20 seconds. Okay. Did it go any further? Maybe a little further. Let's try 30 seconds. Maybe a little further. It's actually not clear. So let's actually plot a few things. Let's actually make our plot a subplot. Let's go to our plot. There's a subplot. We're going to plot our three subplots. We're going to plot our Cartesian trajectory at 3, 1, 1. And we're going to say that this is going to be axis equal because it's our Cartesian coordinates. Then we're going to plot our x and y over time to see how it's actually moving toward our goal. Okay, so subplot 3, 1, 2. So this is going to be the second subplot of 3, all top to bottom. So it's going to be plot. We're going to say tsim. It's going to be all of our times, and we're going to say zsim colon comma 1. I think that our model predictive controller is working. Our x label this time is now time in seconds, and our y label is now our x position in meters. Okay, and we're just going to copy this and turn this into our third plot, which is our vertical position. So this is going to be our third subplot, and instead of plotting our first state, which is x, we're plotting our third state, which is y, and it's our y position. So I run that subplot. Oh yeah, it's moving. Oh, it looks like how many seconds is this running for? Looks like it's only running for 10-ish seconds. It's definitely accelerating, but it's only going for 10 seconds. I thought it was supposed to be simulating for 30, and I'm curious why that is. Did I screw up somewhere? Oh, you all... Can anyone see my mistake? It's on this screen. How long are we simulating for? I wrote 10 instead of what I wanted to do is say, hey, whatever my time span is, it should be that. So this should just literally be from T span 1 to T span 2. Okay. That should solve the problem. Oh, look at that. Look at that. Okay. Hey, look, it goes a little too far. Now it's going to come back. Hey, let's simulate this for 100 seconds. See what happens. Is anyone getting this? Are people having hopeless errors? Look at our model predictive controller. You got that? That's great. Look at that. Isn't it exciting? We're running thousands of trajectory optimizations in seconds. We're doing all that. And to be clear, one thing I want to point out, going back to our code here, or our board here, I'm going to pull up the board for a second. this step here for the model predictive controller, okay, in our simulation, we're executing it for TS seconds, right? If this is on a real piece of hardware, on a real machine, okay, it means that you literally use this for this control input for TS seconds. You literally apply it, right? We're doing it in simulation here, so our simulation is what's like it's like our real system, okay? But on a piece of hardware, on a real physical machine, you would be waiting. You would be doing this step. Where is it? Where's our simulation? This thing, all this stuff was simulation. Here, all this stuff, you wouldn't be doing. You would have a real physical device that you'd be giving your use to. Okay? Great. So one thing you'll notice here is that we are overshooting and undershooting. If this is a PD controller, we would turn up the D gain on that PD controller. But we don't have a PD controller here. All our controller inputs are not decided by a PD control law. They're decided by an optimization. So if we want to change the behavior, we have to change the optimization. And what does that mean? Well, it means we're going to probably be changing either the constraints or the cost. Okay? So right now, our cost only takes into account the position, how close we want it to be to the target. It does not take into account the velocity. So we could penalize the velocity that we want it to be moving be at rest at the end. That's something we could theoretically do. Another thing that we could change, honestly, is the time horizon. We could change the time horizon so that way it's over maybe 5 seconds. Let's just see what happens, because that can change how things work. Whoa! Hey, look at that. So I changed the time horizon, which means that the trajectory optimization is looking further into the future. And voila, where does it end up at? You can see on my screen it ends at X position of 5, Y position of 2. Look at that. Perfect. It gets there. It's looking a little further ahead, so maybe what it's doing is that instead of trying to stomp on the gas and then realize it can't come to rest as fast, okay, it looks a little further ahead and then it performs a little better. Hey, look at that. Model predictive controller. So I just changed the time horizon to 5 seconds. We have an MPC, but that's not fun to look at. Let's make an animation. Okay, so I'm scrolling down to the very, very end here. I'm going to create, so here we're going to say we're going to animate our system. Okay, I'm not going to go for as long. How long was that trajectory for? It's for a long time. Okay, all right, so let's do our quick animate our system. So what we're going to do is we're going to create a frame rate at an FPS. Honestly, this is over the course of many seconds. So how many frames per second do we want? Yeah, I mean, I don't want to simulate it for 20 seconds, but anyway, we'll do it at 20 frames per second. Okay, I want to be able to slow down the simulation or not slow down the simulation. So I want to say I want to speed it up by like 10-fold. I'm going to say, or 5-fold. I'm going to say it's equal to 1/5. This is slowdown of animation. Okay, so what I'm going to do is say that I have a t-anim. This is our animated time, and it's going to be equal to, so it's going to be 0, 1 divided by FPS divided by slow-mo. We divided by slow-mo. Basically, that's just all the way to our final time, which is what, t-sim end. Technically, it should be t-sim beginning, so t-sim 1, t-sim end. This is our animation time vector. I want to show our puck gliding to where it's supposed to go, friends. So The reason I did 1/5 is I want to speed up this thing by like a factor of 5 when we're watching it. Okay, now we're going to get our, let's have our X position for animation. What we're going to say is we're going to interpolate. We've done this interpolation trick before. We're going to say, hey, at all of the different simulation time points we have, and all of the X time points, which are zsim : 1, because X is our first state, we're going to want to know what X is at all of our time points T anim. Okay? Interpolate X animation points for our puck. I'm going to copy this, paste it, and just turn it into Y. Oh, where did I go? Where did I go? I'm going to turn this into Y. And which state is Y, my friends? It's not state 1, it is state 3, and it's interpolate our Y points. So fantastic. So we got our points we want to animate. So now we're going to do an animation loop. Okay. All right. So we're going to do a for iter equals 1 : the number of elements or the length of T anim. Okay. And let's make a new figure as well. So a new figure. First thing we're going to do is we're going to clear the current axes. Okay, and then we're going to want to, well, frankly, we're just going to plot where the puck is. Okay, and all we need to do is plot. We'll plot a little circle. Okay, for where the puck is, and so that's going to be. That should not say X, Y anim. This should say Y anim, friends. No one caught that. All right, except me. So it's equal to X anim iter. So the current iteration of our animation, we want X anim iter, and we want Y anim iter, and we're going to let's make a little red circle. And I'm gonna make it. I'm gonna fill it in so it's not just like a hollow circle. So actually, here's what I'm gonna do: black circle, and so the black outline. I'm gonna change the marker fill. Marker face color, it's called. I'm going to make it red. Okay. I'm going to put this on the second line, and I'm going to say I want my marker size to be large so y'all can see it. I want to say marker size. So basically, I want to make the circle that I'm drawing. I'll make it large. I'll make it 15. I think that's pretty big, if I recall. All right. Then we have to set the axes. Let's do axis equal first. Then we say axis limits. So let's make the axis limits -1, 10, -1, 10. Sure. And one thing I want to do is let's say where the target is. So where is the target? So if we're going to plot multiple things, we're going to have to put our hold on. This here is we're going to plot our puck. So it's going to make a little circle. And then also we're going to have a little X. It's going to be a plot our target. I believe it's called X target or something. X target. Yeah, X target and Y target. That's what we define that to be. And we'll make that a little, I don't know, a black X. Make it a little larger. We'll make it a marker size 15 as well. Okay. And that's the end of our loop. We want to make sure we draw once we're done. I did not put a little pause command for the amount of time, but let's go with this and see what happens. Okay? And that should be our animation loop. So this should run all of our optimizations, and hopefully that actually animates. Hey, look at that. People seeing that? Anyone seeing that? Move this out of your way so you can see the code. Hey, look, it's on the target. Now, friends, I can do you one better. You know what I want to do? I also want to show you the plan that model predictive control is trying to show over time. This should be interesting, okay? So, can I do this? What should I do? What should I do? What should I do? Okay. Here's what I'm going to do. First, I'm going to try to, number one, I'm going to try to move the target over time. Okay? Randomly, this target's going to move around between like 0 and 10 on the X and Y axis. And we're going to watch it try to follow it around. That sound cool? As number one, I ask facetiously because I will do it anyway, even though it's not cool to some people. We're going to have the target just bounce around. Well, that's what we're going to do number one. Okay? So that requires actually a little bit of change. Because right now, if you go up into your code, the target is inside of the cost function, which means we need to update our cost function in each of our loops, just in case the target has changed, right? Right, exactly. So what we're going to do is, what we got right now, it's a functioning model predictive controller, which is awesome. You can see it kind of move around, right? Pretty nifty. So what we need to do is compute these Hessians inside of the loop, just like we did before when we computed the when we computed the constraint functions inside the loop. So we need to do the same trick where we now need to say that we need to create a function called hfunc, okay, which is a MATLAB function, which it takes in what? It needs to take in our target. It needs to take in X target. So first it's H, and our variables that we want to include, we put them inside these curly braces. This is for something called a cell array in MATLAB, but this is the syntax that that MATLAB function wants, okay, to tell it what the inputs are. We say X target and Y target. Yeah. Let's okay. 1 second, friends. 1 second. I'm gonna try to get this right. Okay, because we define it here as a non-symbolic variable. So that means that X target, Y target. So we're gonna want it defined hard up there. So what we're gonna do is we're gonna create some symbolic vector. We'll call it getting decision fatigue here. We'll call this sim target, just to come with thing. So where it's a 2x1 vector, okay? And so here, so this is exactly the same trick that we did before, where we created our X init, okay? This is going to create some sim target. No, I regret doing this. Get rid of that. If you have to go, I understand. I'm gonna time myself for 3 minutes to get this working. Okay. So what I'm gonna do instead, I'm gonna say that X target is a symbolic vector. So I'm gonna say sims, and X target is a symbolic variable, and Y target is a symbolic variable. Okay, great. This all works. So now our cost function has a symbolic X target, Y target. Yeah, and then this should work too. Now I gotta compute the gradient the same way. I'm gonna say that cfunc is going to equal to C X target, Y target. With semicolons there. This creates H and cfunc. All right? Which means we no longer need the H and C down below. Here, we don't need this converted to symbolic to doubles. That's gone. We don't need that anymore. Don't need that anymore. Where we convert these Hessians and Hessians and that to doubles. Gone. We don't need it. If you keep it, I don't think it matters, but because you already have the functions defined. So now all we need to say is that we want to update the cost. So we're going to say that H is equal to hfunc, and we're going to update the cost to be hfunc, and we give it X target and Y target. And the same thing for our gradient, cfunc. So it updates the cost with the target. Now this should all still work exactly the way we worked before, No difference until the animation will probably yell at you. What's F? What's F? Quad prog has F. There's an F somewhere. Data type double F. H-Func? Let me look at H-Func. Or C-Func. Make an error. X target. Y target. What was the error? Requires, it needs to be data type double. So it thinks, I didn't update the quadratic program. That's why. What is C? Oh. What? For some reason, let's try C-Func here. What does this give me? Oh, okay. I know what it is. We need to define the actual target, X target, that we want to, so the numeric value for the target we want to track, we have to be able to substitute it into our, 5 and 2 or something, right? Let's say 5 and 2. Well, this is sloppy, but we'll fix it in a moment. This should make it work, right? That should make it work. So let's say we want to target X value 5, Y value 2. Only the plotting doesn't work now, but perfect. Great. So, all right. Awesome. So we need a numeric value for the target. Let's create a variable. We'll call it X. X target. We'll call it the current target because we want to be able to maybe update it. X target current, right? And we'll call it Y, and we'll say it's equal to 5. Okay. Now let's do Y target current, and let's make it also equal to 5. Okay. So now all we need to do is all the way down at the bottom. So here we want to say this is X target current. Yeah, we're basically there. This is Y target current. Okay. So now we give our Hessian our current targets, and we'll give our gradient our current targets, and that should work. And it just won't plot correctly. So we got to change down in the animation. We got to change X target to current. So let's go down to the simulation down here. X target current. Y target current. That should work. By the way, did not know what X target current is? Did I not? Oh, I didn't spell it right. There's an underscore, I think. X underscore target current, Y underscore target current, I believe. There we go. Hey, look. Still works. Okay. Now let's make it move. So what I'm going to do is I'm going to just have the X target current. I'm going to have it wander around. I'm going to have it wander around. I'm going to have a random walk for it. So I'm going to say randomly it's going to change where it goes. So what I'm going to say, every part of the loop, I'm going to say X target current is equal to X target current plus some random value that's drawn from a normal distribution. I'll just multiply it by 0.1, so it's just a little tiny walk, or maybe 0.05. And I do the same thing for Y. Now, you should see that it's going to be wandering around a little bit. But we won't. But right now, the way we're drawing the target won't move. But you'll see. Okay. So this should work. It just won't look like it's tracking the right place. See, look, it's wandering. See it wandering? It's randomly following a little wanderer where it's trying to go. The only thing is the X isn't falling in the right place. So we just got to keep track of where that target was over time, and it should wander around perfectly, right? Yeah. So we just need to make a vector that stores what all those targets were, right? So that's good. So we need an X target vector. We need an X target vector. We'll call it an X targ vector that stores all the targets, and a Y target vector Okay. So the first element is going to be equal to the y target current, and then we're going to keep updating it. Well, actually, it's just going to be equal to empty to start. Empty, empty. Then we're going to add it each time. So each iteration. So it's going to be. I'm just going to save this. It's going to be xtarg vec. At the end, I'm going to append the current target to the list. So xtarg vec is equal to bracket xtarg vec and whatever our xtarget current is. Okay, now I'm going to copy all that, and I'm using the home keys and then the shift keys to do this. If you're wondering why I'm doing all this nonsense, apologies. It's a little bit hectic. I feel the mood. Okay. All right. So now that should add to the list. We have a list of targets. Now we just need to say, hey, what target are we on? So our animation now is to figure out, hey, what target do we have currently? So let's do that in the interpolation. Let's call this x target animation, right? It's going to be an interp1 along the time vector that we have, and the way we stored it, we stored one of these for every loop of the simulation. So it's going to be from t span 1 in increments of dt all the way out to t span 2, which is the final time. That's our time points, and then we have xtarg vec, and we want to do it at t annum, right? Hopefully that doesn't overshoot. No, that should be fine. That should be totally fine. I think that should be fine. All right. Then we're going to save this, and we're going to copy this, and we're going to say, hey, we want this for y as well. And now we just need to change that to y, change this to y targ vec, and now we just need to plot the animated target. So here it's just going to be xtarg annum. I'm going to grab this, xtarg annum, y targ annum at the current iteration. We might hit one error at the final time. We'll see what happens. All these minimal constraint founds, we can get rid of that. Look at that. Oh, look at the target. Look at the target. It's moving around. It's chasing it down. Let's move this out of the way so you can't see. Look, it's moving around. Isn't that neat? I think it's pretty cool. We can have it wander more by changing it. Instead of rand normalized instead of multiplied by 0.5, a tinier number, we make it a less tiny number like 0.1. We can watch what happens. Look, tracking it around. Moving around. Pretty neat. Look, I know people have left. I just keep doing more things. Like, class is officially over and has been since 10:45. This is all bonus stuff for fun. If you want to see a real fun thing, I'll tell you, this is great. I want to show you what the predicted path is that for the trajectory optimization. So what I'm gonna like when I show you all the animations of the drones having the plotting out a path, I can put that here too. Okay. What I can say is I can store the planned path. Good having you all. Okay. Store the planned path. I'm going to call it xpath store. Okay. It's going to be equal to open close, and our ypath store. Open close. I want to be able to plot every single path that this thing is planning. And you can see what happened. Oh, I missed Jack say that. All right. Okay. I'll put this online here. So I want to be able to plot that over time. It's going to be fun. All right. So I want every column to be the planned X path from MPC. All right. So what that means is that I want to have a bunch of columns for every loop of the simulation that's saying this was the plan, this was the plan, this was the plan, this was the plan for the entire trajectory that it had planned. Now I want to plot out that trajectory in the animation. Can we get that? Yes, we can. All right. And where does that come from? Okay, the X plan path is stored, as you no doubt recall, in our optimized trajectory, all in our decision variables, where all of our X planned paths are here. All of our Y planned paths are here. So if we're looking at here, this is going to be index 1. This is going to be index n plus 1. This is going to be index 2n plus 1. This is going to be index 3n plus 1. This is going to be all the way down here. That there's going to be a 4n plus 1 and a 5n plus 1. Okay? So what we're going to want are all of our X paths. There's going to be 2n plus 1 all the way up through 3n. And it's going to be 4n plus 1 all the way up to 5n. So that's going to be our path. So if we go and say, I want my X path store, is equal to X path store, comma, I'm going to create each column with those different plans. It's going to be W star, which is our optimal set of decision vectors. And we're going to want 2 times n plus 1 through 3 times n. And then we're going to say Y path store. It's going to be, it's equal to 4 times n plus 1 times 5n. And Y path store. Now all we need to do is in our animation, so we'll stop right there. So that should be appended column after column after column after column. And let's finish by putting it in here. Let's plot it. So we're going to plot the path. So here we're going to say that X path, well, let's see, how are we going to get this here? This is going to be a challenge, just the last little bit. Because we're not interpolating along a single vector, we're interpolating along a big old matrix. I might have to just change things to a column and then interpolate along a column. Yes, yes. So what I'm going to do is going to say X path anim is going to be equal to interp 1. Okay, and it's going to be the same time vector, and it's going to be X path store. I'm going to transpose it so that way each row are all of our lists of points at a particular time. You step down the row, it's a new time. Okay, and I believe that the interp 1 that should interpolate like that. And then along T anim. I'm going to try this real quick. See if this works. My thinking is that this should give us interpolated time points for every one of the nodes if I do it like this. So it's going to be Y path anim, Y path store. Okay, and then what I can do in each of these, I can plot a little path. It's going to be X path anim, and I believe it's going to be whatever the current row is, iter comma colon, and Y path anim, iter comma colon. I'm going to make a nice little black line. Let's see if that works. This is all just a bonus to see if we can get this to work. Oh my goodness. Look at that. We did it for a shot. No way. I know some of that was probably opaque to you because make sure you know how to use the interp one function. That takes something, but it's working. Look at that. It's tracking down where it needs to go. Oh my goodness. Let's make it move around more. Let's make it move around more. Let's make it 0.2. And let's make the, so 0.2 for the random motion here. Fantastic. And finally, let's do, this is, I'm just so excited. Let's make this a line width. Make it a thicker line width so you can see it. Line width 2 for the path. Look at that. See the path? Whoa! It's like snaking around. Look at that. I could just keep watching that. Isn't that neat? Other cool things we can do. Notice that every time we solve an optimization, it tells us it's solved, it's solved, it's solved, it's solved. Okay? If we want to turn that off, all we need to do is we need to add some options here. So we're going to say so we're going to say options is equal to optim options. And the solver here is going to be quad prog. And we're going to say the display options that we want none. And we have to tell it these are our options that we want. Okay, the options here. This turns off the display, so we shouldn't see all those optimal solution found, optimal solution found thousands of times. It's gone. I need LB and UB. Okay, we'll get to that in a minute. Boom, boom. We didn't define a lower bound and upper bound, so we just give it nothing there. And no x0. Sorry, this I shouldn't. This is what I get for trying to do something at the last minute. Oh, and I got to put a semicolon there. Try it again. And we're done. Semicolon there. Look at that. I could watch this all day, but I can't. All right, friends, that's all I got. Hopefully that was kind of fun and at least rewarding when you get that. That's model predictive control. Look at that. And it's randomly tracking it. If you wanted to change how it behaves, you could change the cost function. If you want, we can also add more constraints like bounds on the control inputs, which we didn't do. But other than that, it's pretty neat. Thanks all very much. I really appreciate you coming. Have a great one.